So let's look at one more example of a composite function. Given the functions f of x is equal to 1 over x, g of x is equal to x squared plus 1, and h of x is equal to root x, find the following and state the domain. G of f of h of x. This is a double composite function. This means we are taking the function h of x, plugging it into f of x, and plugging all of that into the function g. Well, just as before, same concept. Let's work from the inside out. What can we replace h of x with? Well, h of x is equal to root x. All right. Now we need to evaluate f of root x. That means I'm going to replace every single x in our function f of x with a root x. That gives me g of 1 divided by root x. And to evaluate g of 1 divided by root x, I'm going to replace every single x in my function g of x with a 1 over root x. That gives me 1 over root x squared plus 1. Squaring this fraction, notice that I can square the numerator and square the denominator. Squaring the numerator is going to give me 1, and squaring the square root of x is going to give me x. One thing to make note of here is that, as we'll see in a moment, this value of x has to be greater than 0, right? And we'll talk about that in a second. Again, taking the square root of a number, when we talk about domain, okay, can't be negative, and because it's in the denominator, it can't be 0 either. So that's always going to be some positive value. Now, just doing a little bit of algebra to make it look nicer, we can get a common denominator between these two terms, giving me our final answer of 1 plus x divided by x. All right, so the domain. As we said, we want to start with looking at the domain of the inside function first. Our innermost function is h of x. Well, we have a square root. We know that x must be greater than or equal to 0. Next, we need to look at the domain of the second innermost part. That's f of root x, or 1 over root x. Right? Looking at the domain of f of h of x. 1 over root x. Well, we know that x must be greater than or equal to 0, but because this is in the denominator, x cannot equal 0 either. This just means that x must be greater than 0. And finally, we can look at the domain of our composition as a whole, 1 plus x divided by x. Again, we make note that x cannot equal 0. So to find the domain altogether, we need to find the overlap of these three. Where do they overlap? For values of x that are greater than 0. That's parentheses 0, comma, infinity. Same three functions. Now let's evaluate f of h of g of x. That means we're plugging in g of x into h of x, and all that into our function f. Well, working from the inside out, we replace g of x with x squared plus 1. F of h times x squared, f of h of x squared plus 1 means I'm going to replace every single x in my function h with an x squared plus 1. That gives me f of root x squared plus 1. To evaluate f of root x squared plus 1, I'm going to substitute the entire quantity root x squared plus 1 into my function f of x for every value of x, giving us 1 over root x squared plus 1. Now, is there any algebra that we can do to simplify here? Nope. Our final answer for our composition, 1 over the square root of x squared plus 1. So let's look at our domain of this composite function. Again, we need to start off by looking at the domain of our innermost function. Work from the inside out. What is the domain of g of x? Well, no denominators that are going to be 0, no radicals to worry about. Our domain is going to be all real numbers. Then we need to look at the domain of the composition h of g of x. That is root x squared plus 1. Well, we know because we have a radical, x squared plus 1 must be greater than or equal to 0. Again, we talked about this before. What happens if you square a number and then add 1? Well, that value is always going to be greater than or equal to 0. Again, this statement right here is always true. And because it is true for any value of x, that means that our domain here is still negative infinity to positive infinity. And finally, we need to look at the domain of our entire composition as a whole. Well, we've got a radical and we've got a denominator. We know that the value inside of the radical must be greater than or equal to 0. And in this case, it can't equal 0 because it's also in the denominator. X squared plus 1 must be greater than 0. Still, this is always going to be true. This is always a true statement. Squaring a value and adding 1 will always give me something that is greater than 0. Because it is always true, that means our domain is all real numbers. And so where do all three of these overlap? From negative infinity to positive infinity. All right, there we have our composite functions, our double composite functions in this case. All right, last thing in section 1.9, right? Here's a good skill to have moving forward, especially if you plan on taking calculus next year, all right? Being able to identify when composite functions are occurring and determine an inside function and an outside function. In this case, it says identify two functions f and g such that f of g of x is equal to h of x. In other words, h of x is a composition of two different functions. So we want to try to identify what two functions we are looking at. In some cases, there are going to be multiple answers, all right? But I'll try to keep it as simple as possible. For me, when looking at problems like this, it's important to recognize particular types of functions. Notice I have a square root, okay? That would be a square root function. And inside of that square root, I have a linear function, 9 minus x. If I were to graph y equals 9 minus x, that would be a line with a y-intercept of 9 and a slope of negative 1. Okay, so those would be my two different functions that we could identify. My outside function would be f of x equals root x, and my inside function g of x is equal to 9 minus x. Notice that if we were going to take the composition f of g of x, in other words, plug 9 minus x in for x into the function f, we would end up with our function h of x. Okay, identifying an outer and an inner function. Let's look at this one. H of x is equal to parentheses 1 minus x. Well, what's my inside function here? We have this linear function 1 minus x, and that linear function is inside of a cubic function. So we could say that the inside function is g of x is equal to 1 minus x, and that is all being cubed, being plugged into the function f of x is equal to x cubed. Notice that if we took the composition f of g of x, we would end up with this guy right here. All right, one more that's a little bit trickier. Okay, here we have h of x is equal to 4 divided by 5x squared minus 2. All right. Well, notice that we have a quadratic in the denominator of this function right here, all right? We could separate that quadratic and say, okay, let's make that quadratic a function of its own. That is the function that is on the inside. And what is it being plugged into? Well, the function 4 divided by x, all right? Here we have our inside function, the quadratic, 5x squared minus 2. Our function f of x is equal to 4 divided by x. Notice that evaluating f of g of x, if we were to plug g into f, we would end up with this function h of x.